something showed up in the James Webb Space Telescope's data that no one can fully explain. A faint point of light near the closest sun-like star to Earth, appearing once and then vanishing without a trace. Imagine pointing the most powerful space telescope ever built at the nearest star system to our own. 4 light-years away, so close in cosmic terms that astronomers literally call it our stellar neighbor. And finding something that shouldn't be there. Or more precisely, finding something and then watching it disappear. That is exactly what happened when astronomers turned the James Webb Space Telescope toward Alpha Centauri A in August of 2024. What they detected was a faint blob of infrared light nestled against the blinding glare of a star, so similar to our own sun that scientists call it our closest solar twin. And the signal was real enough to publish, real enough for NASA to call it strong evidence. And yet, when they looked again, months later, twice, it was gone. Welcome to one of the most captivating scientific mysteries of the current era in astronomy. To understand why this matters so profoundly, you need to understand what kind of machine the James Webb Space Telescope actually is. Launched on Christmas Day 2021, JWST represents decades of engineering ambition compressed into a single observatory. Its primary mirror spans 6.5 meters, so large it had to be folded origami style for launch and then painstakingly unfolded in deep space. It operates at temperatures close to absolute zero, just a handful of degrees above the coldest possible state of matter. Because it detects infrared light, heat radiation, and any warmth from the telescope itself would drown out the signals it's hunting. The telescope sits nearly 1 million miles from Earth at a gravitational balance point called Lagrange 2, orbiting the Sun in lockstep with our planet. From that stable perch, shielded from solar heat by a tennis court-sized sun shield, JWST can see the universe in ways no instrument ever has, detecting faint infrared signals from objects billions of light-years away, including the atmospheres of distant exoplanets, the glow of the earliest galaxies, and now, possibly, a world orbiting our nearest stellar neighbor. But Alpha Centauri presented a unique set of challenges. Most exoplanet discoveries happen through indirect methods. Scientists watch for a star to dim slightly as a planet crosses in front of it, or they measure tiny wobbles in a star's motion caused by the gravitational tug of an orbiting world. Direct imaging, actually photographing a planet next to its star, is extraordinarily rare. The reason is almost embarrassingly simple. Stars are blinding. Alpha Centauri A is the 3rd brightest star in the night sky, visible only from the southern hemisphere. It blazes with 1.5 times the luminosity of our sun. Any planet orbiting it would be over 10,000 times fainter. Trying to spot such a planet is like trying to see a firefly hovering a meter away from a lighthouse beam, photographed from across the room. And Alpha Centauri comes with an additional complication. It isn't a single star, it's a triple system. Alpha Centauri A has a binary companion, Alpha Centauri B, a slightly smaller, cooler, orange-hued star, and both are locked in a slow gravitational waltz, completing an orbit around each other every 79.9 years. At their closest, they swing within roughly 11 astronomical units of each other, about the distance from our Sun to Saturn, and at their farthest, they drift nearly to Pluto's equivalent distance. From JWST's perspective, the glare of Alpha Centauri B competes with everything the telescope is trying to see near Alpha Centauri A. Even with the most advanced space observatory in human history, the noise level near this target is staggering. Then there's Proxima Centauri, the 3rd member, a dim red dwarf sitting at an enormous distance from the other two, she notable for being the actual closest individual star to Earth at 4.24 light-years, and already confirmed to host 3 planets. But it was the brighter, sun-like pair that astronomers had always suspected might hold something more familiar, more Earth-adjacent, and so far that had eluded them. The team that changed that picture was led by Charles Bateman, Executive Director of the NASA Exoplanet Science Institute at Caltech, and PhD student Aniket Sanghi, also at Caltech. Their approach was audacious and technically demanding. They used JWST's mid-infrared instrument known as MIRI, a camera and spectrograph that sees wavelengths of light far beyond what human eyes can detect, deep into the thermal infrared, where warm objects glow even in the dark. To suppress the overwhelming light of Alpha Centauri A, they employed a coronagraphic mask, a small opaque element positioned precisely in MIRI's optical path to block the star's disk while allowing light from the surrounding region to pass through. This technique, borrowed from solar astronomy, is how you reveal faint structures that would otherwise be completely overwhelmed by the central source. But coronagraphy with JWST near a binary system isn't a simple matter of plugging in a lens filter. The proximity of Alpha Centauri B, bright enough to partially saturate MIRI's detector at certain positions, added layers of complexity. The team designed a custom observing sequence tailored specifically to this system, taking calibration frames and reference images to model and subtract the expected light patterns from both stars. JWST's mirrors and support structures create characteristic diffraction artifacts, circular halos and spoke-like spikes of light radiating outward, and distinguishing a real astronomical source from those patterns requires meticulous computational analysis. When the data from August 2024 came back, Sanghi noticed something immediately. A faint point of light, a blob, really, sitting at approximately twice the Earth-Sun distance from Alpha Centauri A. It wasn't one of the expected diffraction artifacts. It didn't match the pattern of Alpha Centauri B's scattered light. It was over 10,000 times fainter than Alpha Centauri A itself, but it was there, and it was consistent across multiple processing methods. As Sanghi later described it, the signal simply popped out so clearly. The team's first instinct was skepticism, as it always is with extraordinary detections. They worked hard to explain it away. Could it be an artifact of the optics? No, it didn't match the known diffraction geometry. Could it be a background galaxy or a foreground asteroid? Neither fit. A galaxy at that position would not be expected to appear as a point source in this wavelength range. A passing asteroid was possible, but inconsistent with the brightness and position. The object, designated S1, held up under every test they applied. But something remarkable happened next. And this is where the mystery deepens in ways that have the astronomical community genuinely captivated. The team requested follow-up time on JWST. In February 2025, they pointed the telescope back at Alpha Centauri A. The object was gone. They tried again in April 2025. Still gone. The same team, the same instrument, the same painstaking technique. And the planet candidate had vanished without a trace. "We are faced with the case of a disappearing planet," Sanghi said in the official NASA announcement. It sounds almost whimsical, but the scientific implications are anything but. Here is where orbital mechanics becomes the detective tool of choice. The team ran computer simulations, millions of potential orbital configurations. Constrained by everything they knew, the August 2024 detection, the two non-detections, the gravitational influence of Alpha Centauri B, which limits stable orbits around Alpha Centauri A to within roughly 3 astronomical units, and crucially, a 2019 observation from the European Southern Observatory's Very Large Telescope that had previously hinted at a candidate planet in the same system without ever achieving confirmation. When the team fed all of this into their models, a picture emerged. In approximately 52% of the stable orbital configurations they simulated, the planet would have moved too close to the star during early 2025, swallowed back into the glare, invisible to JWST in both subsequent observations. The disappearance, far from disproving the planet, was actually consistent with the detection. What the models suggest is a gas giant, a world with a mass close to Saturn's, roughly 95 times the mass of Earth, following an elliptical orbit that carries it between 1 and 2 times the Earth-Sun distance from Alpha Centauri A. This is a critical number. The habitable zone of Alpha Centauri A, the region where liquid water could theoretically exist on a rocky surface, begins around 1.2 astronomical units and extends to roughly 1.7 astronomical units. The orbital range suggested by the models places the candidate planet squarely within this zone. That is an extraordinary coincidence of location, even if the planet itself, being a gas giant, is almost certainly not capable of hosting life as we understand it. Scientists are careful and emphatic on this point. But gas giants in habitable zones don't travel alone through history. They can shepherd rocky moons. Their gravity can sculpt the architecture of inner planetary systems. Their presence tells you something deep and important about the formation history of the system they occupy. The implications of this detection exist on multiple levels simultaneously. At the purely scientific level, if confirmed, this would be the closest directly imaged exoplanet to Earth ever recorded. It would be the nearest planet found in the habitable zone of a sun-like star. Alpha Centauri and our own sun are so similar. Similar masses, similar luminosities, similar ages hovering around 4.85 billion years, that comparing their planetary systems would give scientists an unprecedented window into how stellar environments shape the formation and evolution of worlds. Most of what we know about planetary formation comes from studying our own solar system, a single data point. Alpha Centauri a near-perfect twin orbiting just 4 light-years away, offers a second data point. And in science, the difference between 1 data point and 2 is the difference between an anecdote and a pattern. At a broader level, this detection marks a turning point in direct imaging as a science. The signal recovered by JWST near Alpha Centauri A is right at the edge of what the telescope's contrast enhancement techniques can deliver. Independent astronomers not involved in the study have noted that the analysis is painstaking and credible, but that confirmation will require independent detection. The techniques developed for this observation, the custom coronagraphic sequences, the binary star subtraction algorithms, the orbital modeling constrained by both detections and non-detections, represent a methodological leap that will benefit every future attempt at direct imaging of nearby worlds. As Stanimir Mechev, a planet formation researcher at the University of Western Ontario, who was not involved in the study, noted to Live Science, if confirmed, this would be the most significant JWST discovery to date. That statement deserves a moment of pause. JWST has already done extraordinary things. It has captured the deepest infrared images of the early universe ever taken. It has detected carbon dioxide in the atmosphere of a distant exoplanet for the first time. It has revealed molecular clouds and star-forming regions in unprecedented detail. Calling the Alpha Centauri candidate the most significant finding is a strong claim, but it reflects something intuitive. This isn't a galaxy billions of light years away, preserved in ancient light. This is 4 light years, practically next door by cosmic standards, a world we might one day send a probe toward, study in detail across decades, characterize completely with future instruments. The psychological weight of a planet confirmed at Alpha Centauri would be unlike anything that came before it. The team behind the papers, published in a pair of companion articles accepted for the Astrophysical Journal letters, is already planning next steps. Additional JWST observations are the obvious immediate priority. If the planet exists on the predicted elliptical orbit, there are windows of time when it should again be visible, far enough from the star's glare for MIRI's coronagraph to capture it. Each new observation either narrows the orbital possibilities or opens new ones. Meanwhile, NASA's Nancy Grace Roman Space Telescope, currently scheduled for launch no earlier than May 2027, will bring its own coronagraphic instruments to bear on the Alpha Centauri system. Roman is specifically designed to handle the challenges of binary star environments in visible light, complementing JWST's infrared data in wavelengths that could reveal different physical properties of any orbiting planet. Together, JWST and Roman could, if the planet is real, construct one of the most detailed portraits of a nearby exoplanet ever assembled. There's also the haunting possibility that the planet candidate is something else entirely, a transient infrared source, an unusual background object, something in the instrument's behavior not fully accounted for. Science demands that this remain on the table, but the weight of evidence as it currently stands leans toward a genuine detection. The fact that a 2019 ground-based observation from the Very Large Telescope produced a hint of the same candidate before JWST even existed adds a thread of historical continuity that purely instrumental artifacts would not explain. That 2019 signal was always ambiguous, never strong enough to stand alone. But in combination with the August 2024 JWST detection, it suggests that something real has been lurking near Alpha Centauri A for years, glimpsed briefly from different vantage points, never quite staying still long enough to be pinned down definitively. This is the nature of discovery at the frontier of astronomical technique. Planets around nearby stars don't announce themselves with clear, unambiguous data. They reveal themselves in fragments, a dip in brightness here, a wobble there, and now a faint infrared blob that disappears around a corner and leaves the entire community of astronomers leaning forward, waiting. The story of Alpha Centauri has always been one of revelation through patience. It took centuries for astronomers to realize the single bright point in the southern sky was actually 2 stars. It took another 2 centuries to find the third. The first Earth-sized planet at Proxima Centauri wasn't confirmed until 2016. And now, in 2025, we find ourselves staring at the possibility that the nearest sun-like star to our own, our most plausible interstellar destination, the target that every serious conversation about humanity's future in space eventually returns to, might have a giant planet orbiting where liquid water is theoretically possible. The cosmos, it turns out, continues to exceed our expectations, even when we've pointed our greatest instrument directly at it. What comes next is more observations, more data, more analysis. Astronomy has always been a slow accumulation of certainty. But some moments feel like inflection points, moments where the direction of the field changes, where the questions scientists ask shift in fundamental ways. The August 2024 JWST detection at Alpha Centauri A feels like one of those moments, not because it's confirmed, not because it's solved, but because it's real enough and strange enough and close enough that ignoring it isn't an option. The nearest star to our sun has been hiding something. We caught a glimpse of it last August, then it vanished. The telescopes are still watching. That question, what exactly did JWST see? Is now one of the most interesting open problems in all of observational astronomy. And the answer, when it comes, will matter enormously, not just for what it tells us about Alpha Centauri, but for what it tells us about how common worlds like ours might be, scattered across the billion-star landscape of the Milky Way. We are 4 light-years from our nearest neighbor. We just saw something there that we can't fully explain. And the most powerful space telescope ever built is already scheduled to look again. Drop your thoughts in the comments. Do you think the planet is real? What would a confirmed world at Alpha Centauri mean to you? And if you want to follow this story as new observations come in, subscribing is the best way to make sure you don't miss the moment this mystery gets resolved. Because it will. The universe doesn't keep its secrets forever.